Um, so last time, what we were doing at the end of class was to compute the determinant of a matrix that's bigger than 2 by 2. So the examples I was doing yesterday were for 3 by 3 matrices. So again, like in this case, like the idea is to do this matrix of signs. And once you have that, the determinant ends up being computed in the 3 by 3 case of determinants of smaller 2 by 2 matrices. And that is kind of the idea in general, that like the determinant, like for example, from 4 by 4 matrix is computed in terms of a 3 by 3 the determinant of 3 by 3 matrices, and those in terms of 2 by 2 matrices. So it's kind of always like, you know, like the higher levels always refer to the lower levels. So let me show you that in the case of a 4 by 4 matrix, which is kind of like, for practical purposes, it's probably the largest matrix that I would ask you to compute anyways, because like, as you can see, like computing the determinant just takes a little bit of time because there's so many operations involved. So but it is really the same. So let's say that I give you this matrix. It's easier to explain it with an example from the beginning. So I give you this matrix. So again, if you're lucky, the matrix will have a lot of zeros or some zeros. That's kind of like the best you could hope for when computing the determinant. So for the matrix, you write the matrix of signs. So remember, the matrix of signs is literally start with a plus, and from there is everything determined because it just alternates. So just plus, minus, plus, minus, plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, and minus, plus, minus, plus. So the matrix of signs always starts as plus in the top left corner, and there everything else is fixed. So that's oh, just give me a second, sorry. So that's a idea in general, and then you have to choose, in order to compute the determinant, the way we're doing it, you always choose like your favorite row or column. It doesn't matter which one you choose. Obviously, it's just that depending on the one you choose, your life will be made easier or harder. So just to give you an example, you could choose, for example, like row 4. So you can choose row 4. Let's choose it here. So I'm going to use the row 4 to compute the determinant. So the determinant of A using row 4. What does it mean? It means that I look at row 4 in the matrix of signs, or this table of signs, and you just copy the coefficients in row 4 with the multiplied by the sign that appears here. So it is 1 times negative, right? I mean, it becomes -1 plus 0. Okay, this one definitely I will need. Let me see if going to be -1 plus 0. Then minus, I mean, this one would have been like -0, but of course it doesn't really matter. And then plus 5. Okay, I definitely will need more space, so I'll just put it in 2 lines. Otherwise, okay. So those are like the coefficients multiplied by the corresponding sign. So it only flips the sign here of the number if there was a minus sign. In fact, if you want, we can fix this to make it more interesting. Let's put a -1 in front of the -1 here, just to emphasize that. And so in the table of signs, that becomes -1. Okay, so this table of signs will only flip the signs of the numbers that, will only flip the signs whenever there was a minus here. Okay, so yeah, that looks fine. And once you get there, each of these coefficients gets multiplied by a determinant. So you can put here determinant, 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 determinant. Which determinant now is going to be a 3 by 3 matrix obtained by, yeah, you should always, or column, by the way. It can be done with row or column, it's fine. So you have to kind of scan quickly on the matrix to see which row or column has the most number of zeros. So in this case, like kind of 2 was the maximum number of zeros, right? Either in the rows or the columns. So that's why I'm just choosing row 4. But for example, you could have chosen what? Column 4 would also have worked. Column 3 would also have worked. Column 2 would also have worked. Row 2 would also have worked. So in this case, as long as you had chosen one with with 2 zeros, you kind of are saving yourself some time. I'm just doing it here with row 4 just to choose something, but yes, it is the best idea is to do it that way. And I'll after this example, I'll show you that there are a couple of tricks before computing the determinant to create more zeros in the matrix. That also can help you. Okay. So let me, in fact, yeah. So, but once you do that, how do you choose a matrix? And next to each coefficient, you literally delete the row and column to which that number belongs. So for example, in the case of -1, I delete the first column and fourth row because that's where 1 belongs. And you see, you get like a 3 by 3 array of numbers, and that's like the numbers that you put in here. So you put 2, 0, 0, 0, 4, 0, 9, 4, 6. Okay, obviously it doesn't matter too much what goes in here because it's going to be multiplied by 0. So you didn't have to write this. I'm just writing it to show you how you identify the numbers. So in this case, now I delete the second column, fourth row. So you get what? 1, 0, 0, 9, 4, 0, right? And 2, 4, 6. And again, when you copy the numbers, it is easy to just like copy the wrong number because you're copy pasting so many numbers. So it is similar to like the row operations where just like a simple mistake can kind of accumulates. So just try to double check in general that you copied the correct numbers. Again, in this case, it doesn't matter too much because there would have been a 0. So you didn't even have to write this, but I'm just saying like in general, that's what you would do. And then, oops, similar idea here. You delete this row and this column. So you get here. So you get 1, 2, 0, 9, 0, 0, and 2, 9, 6. And the last one is 1, 2, 0, 9, 0, 4, and 2, 9, 4, right? Is that making sense? How I'm choosing the numbers? Any questions up to this point? So once you do that again, minus minus becomes plus, like it becomes +1, so don't even write it. So you just end up with a determinant of 2, 0, 0, 0, 4, 0, 9, 4, 6. And then this one doesn't care, we don't care, we don't care. And then you get +5, a determinant of 1, 2, 0, 9, 0, 4, 2, 9, 4. Okay. And in this case, to compute these remaining determinants, again, you choose like most number of zeros in a row or column. 2 is the best number I can choose from in this case, and 1 seems to be the best I can do here. So I can just choose row 1 in both cases. Like obviously you could have chosen different rows. That's also fine. Or even like a row or a column. But if you happen to be able to choose both rows, it can be more simple to remember than how to extract that coefficient. So in this case, the matrix of signs is plus minus plus minus plus minus and then plus minus plus. So it just gives you. Let's put it with different colors. I'll use green for the first matrix stuff, and I'll use blue for the second one. So you can put 2, the determinant of what? 4, 0, 4, 6. Again, not that you have to put this one because I'll just put them because we're doing it the first time. But obviously, in practice, you wouldn't need to write this because there's a 0 in front of everything. But it's 0, 0, 9, 6. And then plus 0, determinant of 0, 4, 9, 4. Is that making sense? How I chose all these numbers? Again, only the first one really matter because it's the one that's multiplied by something non-zero, but still it's useful to see them all out explicitly, especially the first few times. And then the other one is similar. It's just that remember everything is being multiplied by 5. So this is going to be 1 times 2, which determinant is 0, 4, 9, 4. And then minus 2, which is determinant 9, 4, 2, 4. And then plus 0, which is determinant 9, 0, 2, 9, right? And once you get to 2 by 2 stage, it's easy because you just remember, you can remember easily the formula for, or the determinant of a 2 by 2 matrix. So you just get 2, let's keep using the same colors. You get 2, what is the determinant is this one, 24 minus 0, right? That's like, and then here is 0, 0, I don't care about it. I'll just don't even write it. And then what's this one? This one is 1 times 0 minus 36 minus 2. And then this is 36 minus 12, right? And the last one, the last one you also don't need to worry about because it had like a 0. Okay. And at this point, it's just like being careful to not mess up anything. But this 2 times 24 is 48 plus 5, then minus 36. Then what does this gives you? 24, right? Minus 48. Is that making sense? Yes, yes, yes. So, and then here you can, I mean, if you, obviously, try to choose numbers which are smaller, but like if you want, you can factorize a 12 just to make the arithmetic easier because everything has a 12 in here. So this is minus 3 minus 4, and now it looks a lot better. So it's 12 times 4, and then this is like what? This is minus 7, which this 5 is minus 35. Okay, and then whatever that is. Yeah, I'll choose like in practice, I'll give you numbers, the smaller integers that you can just quickly do it in your head. But I mean, at least this is like a relatively good simplification. Yeah, if this number had been 12, 10, then that would have been, but yeah, like usually, well, it's good at, let me just put what it is, so that you have like the number, it's minus 372. But notice like so the determinant like in general, that there was, I guess like the certain number, like none of the entries here were particularly big numbers, but you're doing so many multiplications, right? That even if you start with all the numbers here were less than 10, right? But it is like what? How many products are you doing? It's like in reality, like you can multiply up to four numbers in the 4 by 4 case when you're doing these calculations, right? Because like there's like the first coefficient that comes from the determinant, and then this determinant of 3 by 3, and this involves like another coefficient, so and then a determinant of 2 by 2. And so in general, like in an n by n matrix, you may end up multiplying n numbers together, and that's why um it ends up giving you, maybe I did something dumb here. Oh yeah, because should have been -8, right? Is that what you're saying? Good, thanks. So, this changes everything a little bit, but let's see. So is this minus, yeah, that's what you're asking me, right? Like, see, this should have been 36 minus 8. So what is that? So it's going to be a little bit uglier because this is going to be what? This is going to be 28, right? And 28 times 2 is 56. So yeah, I don't think there's, is there anything nice that I can factorize here? Well, you could factorize a 4 if you wanted, right? All of them have a 4. And then this one is what, minus 14, right? And then it's for 12 plus. Okay, and then this is what, 9, this is minus 23, right? And then yeah, what is that? That you 5 times 23, that's 115. So it's 12 minus 115. And this is 4 times what? It's minus 103. Okay, this one actually ends up being a little bit easier to multiply, I think. Um, oh, okay. Now I did something. I'm doing some. No, like, is this okay? Yeah. No, I think I'm doing it fine now. And then this is minus 412. So you got 148. You're saying, are we talking about, you talking about here or before or after that? Oh, okay. So, I mean, well, it just depends on whether we agree that this is fine. If this is fine, this is 48, right? And then this was minus 36, and then this one, yeah. Um, you did minus 48 minus 100 in the end. Okay, let's see. Let's see. If someone can check any. Well, yeah, it could be. The only 48 that I see here was positive, right? So I'm not sure where you got. Why would it end up being negative? Let me just double check. Um, A Wolfram there. Oh, okay. Um, you mean so? Let's see. Well, it depends. Maybe if you think about it in terms of the colors, it's a 48 that you is this a 48 that you're getting? Is this the same 48 that we're talking about or not? Well, that one comes from the green stuff, right? So it's kind of just looking at this green stuff. So in the green stuff, I mean, if you do it, well, if you look at the first, if you look at the if you look at the first row in the green stuff, the coefficient 2 starts with a plus, right? Uh, and there was no minus in front of it because there was a minus minus in the formula. Is that I don't know if you noticed, like I had changed the in this matrix, I had changed the number 1 to -1. Yeah. So okay, that makes up the difference. Yeah. I had made like a small change at the beginning so that just to emphasize that this minus will change the sign of the coefficient. So I think that kind of maybe makes up for it. Yeah, because yeah, that's the yeah, but yeah, it's in general. This shows you that like even with simple enough numbers, it can be a bit messy to. I mean, you have to be careful with the answer. Uh, but that also explains why it's good to have like to use a row and column to with a lot of zeros because that kind of makes your life easier. But yeah, let me see because it is 200. Just double checking this quickly. 294. Yeah, and then yeah, it looks fine here. Yeah, I think this is fine. Oh, yeah, and also like, oh my God, this is so silly. No, this is fine, right? Like 36 minus 8, and then oh, okay. Yeah. Okay, yeah. Let's see. Okay, it is easy to write. It's easy here to do some silly mistakes. It's always better to double check everything to make sure that there are no like problems. But well, that's kind of how this is supposed to be um in this case. So it is like it gives you an idea of what you have to do. So just to check here. Yeah. Okay. So but again, like in general, like 4x4 is kind of the max that you would see, and like for our purposes, and yeah, if you have to do something like that, like there will be plenty of zeros on the matrix. Otherwise, like it would be take too much time. But the last thing about determinants that I wanted to tell you was like some sort like final rules or tricks to compute it that actually helps you a little bit in your life. So the first one is a determinant of what's called like upper triangular or lower triangular matrices. Some extra tricks. I don't think I have told you what these are, but you'll see from a picture what they are. So in this case, for these, a determinant would just be the product along the main diagonal. So what do I mean by that? Imagine like I ask you to find the determinant of something like um 2, 4, 3, 0, 2, 0, 0, 0. So if you look something to something like that, okay, there's a lot of zeros. Like you could use like expand along the um first column, for example, or the third row. The thing is like a matrix of this sort is called upper triangular because if you see all the numbers which are non-zero are on the diagonal or above it. So this is called upper triangular because all the non-zero numbers are on the diagonal or on top of the main diagonal. And what I'm saying is that in this case, I mean, that's also again very easy to check because like for these upper triangular matrices, they're just tons of zeros. But it's kind of nice to know as a formula that you can just then multiply the numbers along the diagonal. So it's 2 times 4 times 3, which is 12 times 3, which is 36. Okay. And again, it doesn't matter like the stuff. I mean, it can be done for any square matrix. Like talk about this upper lower triangular. So like a lower triangular will be where the numbers are on the diagonal, the non-zero numbers are on the diagonal or below it. So let me do it in the 4x4 case, like -1, 2, 4, 3, 0, 0, 0, 0, 0, 0. And then you can put whatever you want here. So if you look at something like this, it's called lower triangular because everything that's non-zero can only appear on the diagonal or below it. So you see like the triangle. I mean, there is literally like a triangle here. This is why they have the name triangular. So this is lower triangular. Means, all non-zero numbers are on the diagonal or below it. You can actually have a, I mean, maybe just to emphasize that you can have a zero on the diagonal. That's fine. That's not a problem. So let's put like a zero here just to emphasize that. Um, so if you do that, then the determinant would be like -1 times 2 times 4 times 0, because it's still let's see. Are you talking about the previous problem? Or which 5? You're referring to in the Oh, you mean this 5? Oops, like this one, or or this 5? Are you were talking about the triangular stuff? I mean, if you're asking me about this 5, it's just, yeah, I'm just giving like a some random entries to the, just putting some numbers into the matrix randomly. So I just, to put something, like I just put like a 5. Um, so it's like it's arbitrary. So I mean, the important thing is like for it to be, the really thing that important thing that matter for it to be triangular is that I was not allowed to put something non-zero here. But here below the diagonal, I can put whatever numbers I want. Um, so same goes for here. Like I just made this choice like of -1 completely arbitrary, just to give some illustration. Like so, it was more like, yeah, for illustrative purposes. So like the thing that I'm saying is that when you have an arrangement like this, you can just multiply the numbers on the main diagonal and you get the determinant. Of course, like in this case, since there are so many zeros, you know, it's not too easy to realize that anyways, but it's kind of like saves you some time if you know this result. And so, for example, in this case, it's kind of nice in the sense that because this number is non-zero, right? Since this determinant is non-zero, this means that this matrix would have an inverse, right? That's how you should think about the determinant. So this matrix has an inverse. And since this number is 0, right? This matrix, remember, if the determinant of a matrix is 0, then the matrix cannot have an inverse. So this can't have an inverse. And so, because it would may not have been so clear, like, well, I guess in this case, in the triangular case, it's kind of obvious because then this column, there's no way to make this column the last column of the identity. So it's not too bad to notice that, but I'm just saying, in general, like many times the determinant, like it does give you like a faster way of um, figuring out whether there's an inverse or not. In this case, it was also obvious because again, of the fact that the last column could never be made like the last column of the identity. But I'm just saying this is like an alternative way to think about that. Is that making sense? And then the last three things that I wanted to tell you about this determinant business is how it interacts with the operations on the rows. So the first one is that like the first property, so like the determinant and the row operations. The first one is like a property we had discussed before in the 2 by 2 case. So it is related to what happens if every number in a column or a row is multiplied by some factor. Then you can pull out that factor. So if every number in a column or row is multiplied by the same factor, then you can take that factor outside the determinant. Out of the determinant. So let me just give you an idea of what I mean by that. So imagine that I wanted to compute this determinant, like let's say I wanted to compute this determinant of this 3 by 3 matrix. Of course, one way to do it is just to start simplifying, to just apply directly the formula. A different way that you can do here is that you can, for example, you could notice that every number in the third column is being multiplied by 2, right? So you can factor out a 2 of this determinant. So what I'm saying is that the property says that this determinant is the same as 2 times this determinant. Oh, let me put this in different colors. So 1, 2, 3, and I'll keep the same here. In fact, let me change this. Sorry, I will change these numbers to 3. You'll see why in a second. Is that making sense? So it is like a factorization rule, or it's kind of like you are allowed to take a constant per column or per row. So there was an overall factor of 2 that each of these numbers had, so you can take it out of the determinant. So this determinant is just really twice this determinant. Is that making sense? And then anyone can see like what other factorization you could do here. There's another one you could make. With respect to the new matrix. Yes, at the end of class. So there's another one that you can there's another factorization you can make, right? Like for example, everything in the third row has a common factor of 3, right? So you can pull out that 3. So you can say that this is 2 times 3 times the determinant of what? Now this becomes 1, 1, 1. And then this is 1, 0, 1, 0, negative 1, 2. Is that making sense? So, so this is just 6 times this matrix. Again, it's not a life-changing thing to do, but especially in the determinant, because numbers can get a bit big, it may be more convenient just to work with smaller numbers. So this is one way to do that. by factorizing some numbers out. So it's just like it is easier to kind of try to get the determinant of this matrix because there's more ones than to try to take the determinant of this matrix because they're like, larger integers. Okay, so the properties of the determinant allows you to do that. Is that okay? Any questions about this? So that's the first matrix operation. The second one is really, really useful. It's kind of hard to see why it would be true, but it does work. It's kind of like the most useful one, I think, of these properties with the determinant. It says that if you do like a row operation, like, we had this operation about adding rows when we were reducing a matrix, that will not affect the determinant, the value of the determinant. So here's property 2. If you do a combination of rows, like just for example, like I'll show you what I mean in this case, like 2 row 1 plus row 3 or something like that. This will preserve the value of the determinant. So, and that one is really useful because this one can be used to put zeros in before you take the determinant. So let me give you an example. Let's continue with this matrix. Let's continue with the matrix 1, 0, 1, 0, negative 1, 2, 1, 1, 1, right? So what, if you remember, what would be a way to get more zeros here? For example, you could do minus row 1 plus row 3, right? Let me do minus row 1 plus row 3. And I'll substitute that into row 3. So what I'm saying is that the properties of the determinant, again, this one is not so, this one is definitely not clear. But it just happens to work. The properties of the determinant actually say that the determinant of the matrix is unaltered by doing that operation. So if you get what happens when you do this operation, this becomes one, like this goes away. I mean, that's why I'm doing it, to put a 0 here. You get a minus 1 here, and you get 0 here as well. Okay, and now once you get to something like this, then you shouldn't really even think anymore about what to do. You definitely should just like compute the determinant, because here now, like you, for example, can do like the determinant along the first column, right? So if you do now the determinant along column 1, right? If you do this along column 1, what do you get? You get, I mean, there's so many zeros, right? So you just get 1 times the determinant of minus 1, 2, 1, 0. And that one is easy, right? This determinant is just negative 2. Okay. Is that okay? So since this one was negative 2, if you actually care about the original matrix like I started with in this example, this original matrix is just 6 times the determinant. So the original one would be negative 12. Okay. So this can be convenient to speed up some calculation. So this approach does save you some time when finding the determinant. Is that making sense? So this is actually like perhaps like the most, this and the factorization one is like a good combination of like these two properties do work together very well to help you find the determinant in certain cases. And the last one is like what happens when you swap rows. When you do like an exchange of rows, and the only thing is nothing too interesting. It's just like the determinant changes sign. which makes sense because if you look at the matrix of signs, the signs, like in a matrix of signs, like the rows, to go from one row to the other, you multiply everything by -1. You change the signs. So if you swap signs, that's why more or less that's going to happen. So like the last property about the determinant that I wanted to tell you is what happens when you swap rows. The determinant changes sign. But nothing else changes. So for example, if I wanted to do like the determinant of, I don't know, 2, 1, 0, -1, 2, 3, 1, 1, 1. If for some silly reason I wanted to swap the rows, like you could, for example, do row 1 with row 3, or let's do row 1 with row 2 first. If you do row 1 with row 2, right? If I want to swap those rows, then what I'm saying is that this determinant is minus the determinant of what I get when I swap those rows. I don't like, in practice, this one, it can be useful to have, but it's not as useful as like the other ones, like where you had where really you can create more zeros or just take out certain factors to make the coefficients smaller. But it's just kind of it's kind of useful to see, I suppose. Is that making sense? So again, like there's not too much to say about this property, but swapping rows does give a minus sign. So let me just check quickly if there was something else I wanted to say here. Okay, yeah, for now, this is more or less everything that I wanted to say about the determinant. I don't know, is there any questions about this up to this point? Okay, so the next topic is actually a little bit different from what we were doing right now. So it's about vector spaces. So let's just take because it's a slightly different topic. Let's just take like a 4-minute break, and I'll talk about this vector space stuff like for 30 minutes, around 30 minutes, and I'll give you, and then we can take the quiz. So yeah, it's just slightly switch of topics. So let's just take a quick break, and then when we come back, I'll tell you about that. Okay, yeah. So as I was saying, I'm going to tell you now about vector spaces. Um, so can be one of the tricky parts of this is probably the most like abstract part of the course. Like, so it can be a little bit tricky. So we just have to go a little bit slowly on this stuff because it can be confusing. So let me start by just comparing two equations. So let's start here. Let's just compare these two equations. Let's compare like x plus y plus z equals 1 versus x plus y plus z equals 0. So just to emphasize what's the difference between them, I'll put like a color, different color here. So the only difference between these two equations, right, is that in one equation, the number is being set equal to 1, right? The coefficient. And in the other equation, the number is being set equal to 0. So there are many ways in which these equations are not too different, right? I mean, even the coefficients are the same, right, in front of each variable, but there's another sense in which they are very, very different equations. So I'll try to explain why they're different in a way that now we care. So anyone remembers like how this equation looks like? That's sometimes a good place to start. So if I just tell you what's like how does this equation look like on the like how we talked about this at some time before on the course, right? Like how certain of these equations would look like. So anyone remembers in this case what you end up getting? Well, we can actually I can actually plot it for you if you want to see it. So if you take something like x plus y plus z equals 1, right? You get this. And what was the name that we gave to this sort of thing? You get a plane, right? So the first equation is a plane, right? Which would you see here. And the second equation, x plus y plus z equals 0, right? It's also another plane. Like, in fact, it's a plane. I don't know if it's so clear to see. It is a plane that ends up being parallel to the other one, right? The pink and the blue planes are parallel, essentially because the coefficients are the same in this case. You only need the coefficients to like be constant multiples of one another, but that's a longer story. So you get two planes. Like each equation gives you a plane. The planes happen to be parallel. So what's so different about these two equations? Well, the difference is that one of these equations, or one of these planes, if you see it, like maybe I can zoom in a little bit, one of these planes passes through the origin, right? And the other one does not. So let me write that down first, because that seems like not like a big difference, but it actually is like an important difference. So both are planes. So the first one is a plane. Both equations are planes. Are the equations of planes. But only one of them passes through the origin, right? So here is x plus y plus z equals 0. here's like x plus y plus c equals 1. So is that okay? Is that making sense? The origin being the vector the 0, 0, 0. Okay, and so why is that a difference? Because so here's what happens. What's the difference between these two when one has the origin and the other does not? So just to make this more concrete, let's start with this equation. Let me see if I can draw something somewhat accurate. So yeah, it's kind of hard to draw it so that it doesn't look like it contains the origin. I'm trying to do that. So I mean, I'll draw it like as I had it like here. It's a little bit deceptive, but it's okay. So I have this plane, and what happens now is that you can have a vector on the plane. So what's a vector on the plane? Like for example, let me see one that kind of looks okay. Here's a vector on this plane. Let's call this v1, which is I'm thinking of this as xyz, by the way. So here's v1. I'll use a different color. So v1, which is 0, 1, 0. So this is a vector that belongs to the plane, right? Or the endpoint of this vector, the head of this vector belongs to the plane. So the endpoint or the head if you remember like what these vectors represented, that's like the vector that starts at the origin, right? This vector represents a vector that starts at the origin and ends at the point 0, 1, 0, right? So that's why this is why this belongs to the plane, because if you look at the plane equation, the condition for being in the plane is that if you add x with y with z, you get 1, right? Is that making sense? So 0 plus 1 plus 0 is 1, which is so it satisfies. Is that okay? And here's another one that belongs to the plane, another vector that belongs to this plane. Let's call it mine. Let's see. Oh yeah, I want this to be. Let's say okay, like 1, 1, -1. If I do 1, 1, -1, that's somewhere in here. just imagine that it goes below the XY plane. So it's somewhere in here. So it's V2. So this one also belongs to the plane because the condition for belonging to the plane is that if you add their entries, you get 1, right? And so if you do 1 plus 1 plus -1, you get 1, which is the plane equation. Is that making sense? So these two vectors belong to the plane. Is that okay? So far, so good? Oh, let's see if I can do it. Okay, and but now what happens if we do and now I'm about to show you how this looks like on GeoGebra. But what happens if we add these two vectors together? What happens if we do V1 plus V2? What do we get here? We get 0, 1, 0 plus 1, 1, -1. And what is that equal to? Oops. That is equal to 1, 2, -1, right? And the question is now, is this new vector in the plane or not? So you get 1 plus 2 plus -1, and that gives you 2, right? But the condition for being in the plane is that when you have the entries, you get 1, not 2. So this new vector, the sum, is no longer in the plane, right? So this new vector. So just to emphasize that, I mean, it's kind of hard to draw here. It might look something like this. This is where V1 plus V2 is. It's outside the plane. Is that making sense? So just to give you an idea of how this looks like on GeoGebra, let me see if I can show you. So let me hide the second plane. So I had one vector, which is this vector that you see here. That's like what corresponds to V1. Then I had another vector that was corresponding to V2. So this is where you see that each of them terminates on the plane, right? They're being called U and V in this GeoGebra because that's just easier to name them that way. So you have these two vectors that terminate at the planes, and then you had this other one, 1, 2, -1, with W, which is U plus V. Okay, so if you do U plus V, which is adding up these vectors, these two black vectors to get the other one, you see that only 2 end up being on the plane, and the third one, which is the sum, kind of kind of takes you out of the plane, the sum. So what happens in this first plane equation is that when you add up two vectors, the resulting vector may no longer be in the original plane. So let me write that down because that will be useful in a moment. So So what I'm trying to say, so to summarize the situation, for x plus y plus c plus 1 equals 1, you may start with two vectors or two solutions to this equation. You can have two vectors. Or if you want to prefer to think about it in terms of solutions, you can also think about any solutions which satisfy the equation. But adding the solution no longer does. But their sum no longer satisfy the equation. Okay. But the question is, what happens in the case of the other plane? So let's go now to the second plane. So now let's study the plane. Now let's look at this at the plane x plus y plus c equals 0. This one is also easier to draw. We can draw it like this. Again, this is x, y, c. So you could have like a vector, let's call it, just to use a different name, I'll call it u1. I could have a vector called u1, which is 1, 0, negative 1. So it's kind of like here. So this vector, if you look at this vector satisfies, if you add their entries, is 1 plus 0 plus negative 1. So that gives you 0. So this vector belongs to the plane, right? Or when I say that the vector belongs to the plane, I mean that its head or its endpoint, where it terminates, belongs to the plane. And let's take another vector like that. Like if I take u2 to be 0, 1, negative 1, it kind of looks somewhere in here. Here's u2. And then you do 0 plus 1 plus negative 1. And that gives you 0. So it satisfies the condition of belonging to the plane. And then if you add them together, if you take their sum, u1 plus u2, which is 0, 1, negative 1. Oops. Sorry, it's 1, 0, negative 1 plus 0, 1, negative 1. What does that give you? It gives you 1, 1, negative 2, right? So if you look at that, it is just kind of more like a negative in the c direction. But does it belong to the plane? Yes, because if you added their entries, you get 0 again. So in this case, for this plane, adding two vectors or adding two solutions gives you a new solution or a new vector, which still satisfies the original plane. So in this situation, for this case, adding two vectors or solutions which satisfy the plane equation produces a new vector Okay, so the difference between the two planes, again, they geometrically are like planes, but the first one like fails to kind of preserve like the solutions in the sense that you can get to when you add up two solutions or two vectors, you may no longer end up with the solution of the original equation. But the second one does continue to have this property. So from that perspective, the second one is going to be more useful for our purposes because it will have this like property of preserving the solutions. So let me just go to GeoGebra to show you that again. So I can show you this equation now. See, so this is one of the vectors. The other vector is this one's 0, 1, -1. Okay, so now I'm showing you two vectors on the plane, these two black vectors on the plane, and then I'm adding them together and the new vector remains on the plane. So that's the difference between the two. That and in fact, like in this case, like kind of like the entire vector is also literally belongs to the plane. In the previous case, if you look at the picture, only the head, right? So that's another difference here. Like all of it can be kind of drawn on the plane. So that the difference between something preserving the sums or not is what we will define as a vector space. So let me just give you like that definition. Like I mean, I'll repeat it next time, but just to at least write something quickly before we finish today. So a vector space so what we will do is define a vector space will be like a set or a collection of objects or which have the property which satisfies some equations. Have the property usually these vector spaces are called V in capital letters, uppercase V. So it will have the property that if you take two vectors or two solutions of this equation, the sum continues to be a solution. If you take two objects which satisfy the equation, the sum continues to satisfy the equation because some of these to satisfy the equation. So kind of like the solutions you can continue to create solutions by adding up the vectors or the objects. And again, I'll give you more examples next time. And the second property is just that if you take a solution or an object that satisfies that equation and you multiply that object by a number, then that new object satisfies the equation. So if you take, it looks a little bit too weird, but we'll see next time that is not so odd. So if you take an object which satisfies the equation, and multiply it by a real number, by a real number, then the new object, then this new object, then the rescaled object, because that's what you're doing, rescaling it. Okay, so again, it looks a little bit odd the way I'm writing it, but next time we'll start from here and give you some examples of what I mean. But again, vector space is kind of something where like you have some equations that are being solved or satisfied. And the point of a vector space is that if you take solutions to that equation, you can create new solutions by just adding individual solutions. So it's kind of like a way to, it's like a nice way to generate solutions out of old ones, which doesn't happen all the time, as you just saw, because in the first plane, when you had like a 1 on the right-hand side, you could take those solutions, but then when you add them together, that may not satisfy the original plane equation. So it's like a very important concept. And again, we'll spend more or less all of next week just talking about that. So that would be the main focus for the next 4 classes, I think. So just, but so yeah, I'll restart here next time with this stuff. So just quickly, am I sharing my, let's see what am I sharing? Oh, here it is. So yeah, I'm about to, oh, I forgot. I posted the solutions to the exam here on the module. So, you know, if anyone wants to check it out, you can. If you have questions, you can let me know. I tried to write some comments on what you did when I was creating it, but you can still ask me. You can email me or ask me about it another time. Just check the solutions if you want. And then for the quiz, when you take the quiz, when you all upload your solutions, I kind of created the upload assignment for the quiz on Gradescope. So if you can upload the solutions of Gradescope for this quiz, that would be fine. So just in case you don't find it as a separate assignment. So yeah, so now you can take the quiz at any time that you want. So question on the problem 4 of the problems. So problem 4 of the problems, you mean what does it mean? You're talking about the problems I recommended on the quiz. So what was problem 4? Do you remember the problem on the PDF, the number, or was it literally problem 4? Oh, it was 4 on the PDF. Let me see. Let's see. So problem 4. Okay. Oh, yeah, you should have uploaded to Gradescope. It was this one about the finding the values of P that make the vectors linearly independent.
Hi, Professor. Yes.
Okay, yeah. So in this case, you had to, I don't know if you saw the solution, but you had to create like you put like these three vectors as a. The quiz is still unlocked on browser. Yes, the quiz is still unlocked on browser. It says that the upload is in grayscale. Let me check if I already made it available. Yeah. Now you should be able to look at the quiz, but yeah, it's unlocked on browser. It's just that
Oh, sorry.
Mhm.
So for problem 4, I was looking. I saw the video and I row reduced everything. For the matrix, but I saw the last one. It becomes linearly. You get like the infinite solution, like the last row then 0, 0, 0, 0. So and it said to find P in terms of it being linearly independent. But if you have an infinite solution, wouldn't it be linearly dependent for the homogeneous?
Okay. So right. Yeah. So it has to be like I don't know if I hope I didn't make any mistakes. So when you set it up as a matrix, okay, let me put it on the PDF because like it can be confusing. So
I took it as like all the column vectors into one matrix, and then I also tried setting that to A, and then I set it equal to the homogeneous 0 vector, so to see if it's
yes.
And then when I reduced everything down, I got it as linearly dependent because the last like row became 0, 0, 0, 0.
Well, that's where you have to be careful. But yeah, you were doing it the right way. So let me put here's problem 4. So in problem 4, yeah, if you put it as a matrix, you get 1p, right? 2 plus p plus 1 plus p plus 1, 2, p minus 1, p minus 1, p, right? So yeah, you can put it when you put it to the homogeneous system, homogeneous system, you can put 0, 0, 0, 0. It doesn't really matter too much because there are a bunch of zeros, on the right side. So you will never get anything besides 0 when you reduce it. Imagine that you reduce this, I don't know, blah, blah. You reduce this and somehow, I don't know, you get some junk here, but the last row is like 0, 0, zeros, right? Which sounds like what you were getting. That you have to be careful because in this case, how many rows are there? There were 4 rows, right? So that means like if you just get like a row full of zeros, if you just get a row full of zeros, that could mean that you have 3 non-zero rows, right? So that means that the rank in this case would have been 3, right? And because the rank is the same as the number of columns, right? In this case, there are only 3 columns, right? That means that actually the system has like a unique solution, the homogeneous system.
Oh, I see. Okay.
So they are independent. Just to answer Neil's question in the chat. Yeah, if the homogeneous system has a unique solution, they're linearly independent. If you had like 2 non-zero, if you had, for example, 2 0 rows, right? Then the rank drops to 2. Once the rank drops to 2, that's less than the number of columns, and then they're infinitely many solutions, and that's linearly dependent. Is that making sense? So yeah, you just have to be careful because this is like a non-square matrix. So when it's non-square, it is a little bit more tricky because of that. So it's not just counting the number of 0 rows. You have to count the rank versus the number of columns. Is that making sense?
I have a question.
So
like to solve question 4, but what you wrote here is you have written like 4 zeros on the right hand side, but in the video you have written p0 p0.
Well, maybe I'm not sure. Was I solving the same exact problem on the video? I mean, there could have been P0, P0. Oh, I think maybe was there like a second part to that question, maybe that I solved in the video. I mean, like as I wrote it on the PDF. Let me check the video, like if I can find it quickly on YouTube.
I mean, like in the review video, lecture 9, at the very end of the video.
Okay, let me see. I should be able to find it in this. Oh, okay. Give me a second. What am I doing here? Playlist vid. Okay, so we're talking about lecture review. So it was near the end. Okay, good. So let's see. I have to mute myself. Okay, yeah, I'm already muted. Okay. Oh, okay. It's just that yeah, I don't know if you can see my Google Chrome. It just had it's just that when I solved it in this on the video, I had two parts to that problem, right? Part A, part B. So part A is the one that I was solving. It's the one that's on the PDF. Part B is like, I mean, that's why in part B I was putting P0, P0 because that was like a second thing, but it was not. I mean, if you,
I mean, like, but the question, question for on the but question for on the PDF only has 1 point, but over here,
right? It's on.
Yeah, but over here it says you have 2 points.
Right. In this question, on the video, it's yeah, I just like I may have come up with a different. I don't remember. Yeah, but the PDF only had one part. I agree. Yes.
So PDF is should I write P0 P0 or 0000?
The PDF was just part A of this problem, so it was just with 0000. It was all with bunch of zeros. Yeah.
But what's the P here? You wrote P0 P0 for the as the right hand side.
Well, it's just like, I mean, it's just a vector. It's so I'm just saying, like, here's like a vector that depends on P. Is that a linear combination of the other ones? So it's just like, it's kind of like similar to, I mean, it doesn't like, again, like that was not on the PDF originally, the way I wrote it. But if you had like P0, P0, it's just like, I'm just trying to make available the iPad. Saying, if you like, yeah, in part B, which is not, I guess it's not, it was not on the PDF. If you like, if this was asking to whether P0, P0, is a linear combination of those three. Yeah, that's just like a vector. That's just some vector that depends on P. I don't know what P is, right? So but you kind of have to, like, the point of the problem was to give values for P for which, like, to say for which values of P that could be a linear combination or not. So it's just like you start reducing this matrix. Like, what does it mean for this to be a linear combination? That means that this system must have a solution, right? So
Yeah.
you need this to have a solution. So you just have to start reducing the matrix to say for what values of P this has a solution. And you need to see for which values of P this system has one or infinitely many solutions. That's what you need. So it's kind of similar to the exam problem that I had given, where it was like, a system of equations that depended on A and B. And I asked, when does that system have like 0 solutions, 1 solution, or infinite solution? It's like the difference here is like everything is in terms of P. So you just have to start reducing the matrix to see for which values you get.
So
you get one.
I mean, like, so can I just use P0 P0 as the final vector for question 4 on this quiz?
Well, only if I was asking, like, only if I'm asking when, like, is it in this part, like I was asking specifically when is this vector a linear combination of these three, right? In the first part of the problem, it was just asking when are these three vectors linearly independent. So if you're just asking when it's linearly independent, you always put 0, 0, 0. But if you're asking for a linear combination, then you put like the vector that you cared about. So it's not, I mean, if I Uh-huh.
So if you're asking about like whether those are linearly linearly like independent, so they're like linearly independent if they have a unique solution, or did I get it
Correct.
wrong?
If there's like correct. If there's like a unique solution, but when you put 0, 0, 0, 0, yes, exactly. It's just that this part, this part is not on the PDF as I wrote it, so I wouldn't ask for this one, P0, P0. But I'm just saying, if I had asked for that, then yeah, you had to put P0, P0 here. But the question on the PDF was only about the linear independence, so it would only have been about this.
I forgot what I mean. Sorry, I forgot. I mean, like, what's the condition for it to be linearly independent?
The condition for it to be linearly independent is that AX equals 0 has a unique solution.
Okay, thank
So
you.
that's linearly. Yeah, no worries. Is there anyone else left on the chat? Yeah, I don't know if there was another question that I had needed to answer. Okay.